There we go. Okay, so like I was saying, so we're going to solve for our resistance total first. First thing we're going to go through is coming off of our power supply is we have R1 by itself. That's going to be in series with R2 and R3 in parallel. Then as we continue to come around here, we're going to have in series again, because we have one common connection point, we're going to add together R4 in parallel with R5 in parallel with R6 in series with R7. So longhand, that's what our formula is going to look like to solve for our R total. Now we'll go through and we'll solve each of these individually. So this group right here, we'll call R equivalent or R parallel 1, however you want to put it. And we'll label this guy as R equivalent 2, just so we have a label that we can assign and kind of condense this stuff down. So the first thing we want to solve for is what is our R equivalent 1? So again, how many resistors do we have? 2. So we can either use the reciprocal method or we can use the product over the sum. Either way, doesn't matter. And you can divide it by 2 since they're the same. So this equivalent becomes 1.1 kiloohms. So in this case, we could use any one of our three methods for being able to find the resistance. So this branch is going to be 1.1K. So now we're trying to solve R equivalent 2. Well, remember like what I was saying earlier with our order of operations, we want to do series first and then do parallel functions. So the first thing we have to look at is this R6, R7 relationship. Since those are in series inside of a parallel network, we're going to have to add those guys up first. So this one we could even call our R equivalent 3, which is just simply 3.5 kiloohms. Because we just add the 2K and the 1.5K, add them together. So now we have a 1.75K, a 3.5K, and a 3.5K all in parallel. How are we going to solve this equivalency? Do what? Yeah, we could use the reciprocal method for all of it. What else could we do, Max? Yep. So in this case, because we have two 3.5 kiloohm resistors, again, we can apply this method. If we have the same number, or the same value, we divide by that number, and that's going to take all those similar ones out. So in this case, we'll combine these guys together, and that's going to give us a 1.75K ohm. Now we have two 1.75K ohm in parallel. We divide that by 2. It's like I did this on purpose. Once in a while, I'm nice like this. So, when we combine these two guys together, so we end up with 875 ohms. So 1750 divided by 2 is 875. So now we have all three parts of this that we can put together. So our R total is going to be equal to 125 plus the 1.1K plus the 875. $2.1K. Yep. Okay. So everybody see how we got that? Any questions about trying to get there? Okay. So again, our total resistance is all the resistance in the circuit. So we have to look at everything, what's in parallel, what's in series. So we have R1 here that only has one resistor, so it's going to be in series with these two. When we combine those together, that's going to give us one value in series. We have these four resistors, which are in parallel. So these two are going to add together and form one value, and then we're going to have three resistor values in parallel. And then we're going to combine those all together. So for this set, since they are the same value, we can use one of our I guess shortcuts, I guess you could say, our formulas. So if we have resistors that are the same value in parallel, we count the number of resistors we have of that same value and divide the one nominal value by that number. So in this case, we take the 2.2, we divide it by 2, because there's two of them. Yes. Yep. Yeah, so if you have any number of the same valued resistor, you can just divide whatever the one value of it is by the number of resistors, and that will give you the same value. So here we end up with the 1.1 kilo ohms in, now that's all combined down to one value. We look at this value, or this grouping of parallel resistors. We have these two that are in series, and then that's a branch with everything else. So this was if we had split these up, you know, when we're making them in lab. So we needed 3.5K, we didn't have one. We had a 2 and we had a 1.5, we could use that as the same thing. Okay, so 2 and 1.5 is 3.5K. We have a 3.5K in parallel with a 3.5K. Same rule as what we have here, we can divide that in half. Since we have two of them. 3.5 is one, goes down to 1.75, then we have a 1.75 in parallel with a 1.75. Again, we can apply that rule where they have the same value, we divide by that number. And so that gives us the 875 for our second parallel branch. Then we just add everything together. So now we have a total of 2.1 K ohms. Does that make sense now? Okay. So now that we have that, we need to go through and solve for our various parts. We can go through and we can solve for current and use current to solve everything. We can go through and solve voltages and use voltages to solve everything. Which way would you guys like to go? Voltages? Okay. So for voltages, remember in a series circuit is when we can use voltage divider. So now we have this broken up into three individual resistors, the 1.1, the 875, and our 125. So we can find the voltage of R1 by simply taking the value of this guy divided by the total and multiplied by our total voltage. So we take 125 divided by 2.1K, multiply that quantity by 20, and that's going to give us our voltage drop across this resistor, which is 1.19? Huh? Yes. Okay. So this V R equivalent to, so remember we're going to take this whole thing combined together because once they're in parallel, they're going to have the same voltage. So we're going to take the 875, we're going to divide that by the 2.1K, multiply that by 20 volts, and what voltage is going to give us for this other parallel branch, for the bottom parallel branch? How much? Everybody good with those? Where are we at? Now, we can get the voltage across this other branch. We simply add these two guys together and subtract that from 20. So the voltage drop across our R equivalent 1 is equal to the 20 volts minus the 1.19 minus the 8.33, or yeah, 8.33 volts. It's an equals. And so what's our voltage drop across that first parallel network? Everybody good with how we got that? Any questions about how we got there? Okay. So now that's going to give us the voltages across all these guys. Because R2 and R3 are going to have the same voltage here. R1's by itself. And then R4, R5 is going to have the voltage. But what about R6 and R7? Yes. So VR6. Again, we're going to take, so in this case, we're going to look at just this network right here. What's in series with the same components and what voltage are they sharing? So in this instance, we will have the 2.0K divided by the 3.5K, because that's our total resistance in this branch. And that's going to be multiplied by the 8.33 volts. Because both of them together are going to share that 8.3, and they're going to split that apart between the two of them. So VR6 comes out to be how much voltage? Good? Okay. So VR7 is going to be equal to that 8.33 minus the 4.76. It's going to give us 3.6-ish. So VR4 is 8.33 volts. VR5 is 8.33 volts. VR6 is 4.76 volts. And then VR7 is 3.57 volts. Any questions, comments, concerns about getting the voltages? We good there? Okay. So now that we have our voltages, we want to look at getting our currents. What's going to be special about the current going through R1? It's the same as the total current. So IR1 is going to equal I total. And we can double check that. So what I want you guys to do is take the voltage drop across R1 divided by the 125 ohms. And then somebody else take the total voltage, the 20 volts, and divide it by the 2.1 kilo ohms. For R1, using the R1 method. Okay, and then using the total, should be the same. So like I said, there's always these double checks. And the reason that we know the total current is going through here, because there's nothing in between the battery and our resistor right there. So that's going to have total current. switch colors so that way we can see the difference between our values. Okay, so what was that value? Okay, now we have that much current coming through this direction. It's going to hit this node, and we're going to split. So we can do one of two ways to solve the current on each of these individual branches. We can take their individual branch voltages divided by the resistance, or we could also use current divider. But there's also another way to do this. Yeah, because these resistor values are equal, they're going to completely split. So we're going to have 50% of this go here, 50% of this go here. If we had 3 branches, we would see a third of it going through each of those branches, and so on and so forth. The more branches you add of the same resistance, they're going to have the exact same current. So what is this current through these branches? .583. You good with those? I just realized I had a mistake in my math. I dropped a value, so my numbers are just slightly off. But that's okay. So now we're going to have those currents flowing through here. When they hit this node, they're going to split up. So we're going to have current go in this direction and current go in this direction. Okay? But again, this total current is what we have coming in because we have the total current going into this branch. It splits apart, comes back together at this branch. So we're still going to have the total current that we're going to be splitting up between these 3 branches. So again, we can do either our current divider or we can just solve it using Ohm's law. Either way. This one's going to be a little bit different because now we've got 3 different branches. They're not all sharing the same thing. But we should expect to see, these ones should be twice as much as that current individually. So that's one of the things we should be looking for too, is these relationships between the resistors. How much more bigger or smaller is the different branches? That's going to be how much more bigger or smaller our current is. So what is our current going through R4? We take the 8.33 volts divided by the 1.75K. Setup for current divider it's similar to the voltage divider, except for you take your total current and then you multiply it by your total resistance divided by the individual branch resistance. So in this case, remember our equivalent is 875, so that value would go on top, and then on bottom would be these individual values. Well, no, it would be, so for current divider, let's say, so R4, so IR4, using current divider, we're going to take the 9.52 milliamps, we're going to multiply it by 875 over the 1.75K. Because we take our I total times the R total divided by whichever resistance we're looking for. That's our formula. Yeah, each branch. So when we run this through, what do we get? Okay. And sorry, I said this backwards. We should see twice as much current here as we do through those branches because we have half as much current. I apologize for that. Okay, so now that we know coming through this branch, we've got 4.76 milliamps. So if we have 4.76 go in this direction, how much current do we have splitting at that node? 4.76. Now, that 4.76 is going to hit this node, and it's going to split again. How is that going to split? Evenly, because again, we have 3.5 k ohms of resistance. So even using Kirchhoff's current law, we can track this current as it goes through each individual node. So in this case, we're going to have 2. How much? 3.8 milliamps. Does that make sense? So we're kind of using a combination of everything that we've learned as we solve this guy. And we do keep bouncing back and forth, just kind of make sure you guys are familiar with all the different types. So using this method here, this is Kirchhoff's current law. We know how much current we have going in. We're going to split it out. We can solve for how much current's going this direction, and then how much is going left has to go this way. There's no other place for it to go. It's going to hit another node and split again. This is going to come in handy when we get into our loaded voltage dividers, which we're going to be covering today or tomorrow. So what's our current going through R6? 2.38. Because these two guys are in series, so they're going to have the same current. And we can go back through it. We could double check. You take your 2.38 milliamps times your 2 k ohms. That's going to give you 4.76 volts. Or thereabouts, depending on how you round it off. So then with the same, if we were going to continue with our Kirchhoff's current law, so we've got current coming up this direction, we have current coming in here. So the only direction it has is to go up. So now we have our 4.76 milliamps going up through there again. And then when we hit this node, we're going to combine back together. And we better get back to our I total. We're back to our original value that we started with. So we should have the 952 coming out, 952 going in, and we should be able to account for every bit of current and every bit of voltage in these circuits. That's one of the cool things about series parallel circuits, is we can actually watch and see how this is going to split and make calculations and assumptions based on these. Okay, so if we wanted to build this guy, now we want to solve for powers. So here's what we're going to do. We'll go Jameson, solve for power for R1, Kately, R2, Seth, R3, Spencer, R4, Fallon, R5, Carson, R6, and where the hell did your name just escape me? Zach. Zach, solve for the power for R7. I apologize. I'm trying to learn the names, and it's hard with masks on. It really is. That fix it?
We did after class like 30 minutes trying to figure it out. It's like a rocket science, and it's chicken scratch everywhere, and then we just do it, and it makes so much more sense.
So yeah, so here's the thing too. This is rocket science. This could be the ignition circuit to light the rocket. It could be. Yeah, you're good. The rocket never fired, so. Houston, we have a problem. All right, so powers, Jameson. Okay, so as we're looking at this, this should probably, it's got the most current, maybe not necessarily all the voltage, but, we should kind of, well, we should see these patterns emerge. R2. How much? 0.16 watts or milliwatts?
Oh, milliamps. Wait, no. Wait, no, I think so it's current, right?
So it's current times voltage.
Oh, that explains a lot, okay.
Okay, we'll come back. Kaylee? R2? It's 49.
It's okay, I thought you said. I don't know, things are kind of jumbled everywhere.
Right, that's why I was doing different colors, and I do apologize, things kind of get jumbled through there, but that's why I came back.
Okay.
Because why is this one going to be the same as this guy?
I'm not sure how to.
Because it has the same current and the same voltage. So they're going to be the same value. That's why I came back like that. Again, it's just voltage times current. Okay?
So I multiplied 8.23 volts by 4.7 milliamps to come out with 39.65 kilowatts.
Okay. R5?
So I multiplied 2.38 milliamps by 8.22 volts, and I got 19.825 kilowatts.
Okay. R6? Yeah, by its voltage. Okay, and R7. Okay. So when it's all said and done, we could easily build this circuit in lab and not have any issues. Because nothing is even getting close to 250 milliwatts, which is the resistors you guys have. So we're good there. The voltage of R6 is 4.76 multiplied by the 2.38. Yeah, 11 point what? Yep. Okay, so what Fallon was noticing there is these two should have added together to equal this guy because, again, we have the same current, and together we have the same resistance, same voltage drops. So that was a good catch. Those are the things we want to be looking at. If something doesn't quite look right, start comparing it. Okay, where does it fall in line to everything else? Is there something that's closely related to it that's going to add be one way or the other to that to kind of double check your answers. There's not going to be anything like this on the quiz. There might be like something like this for a bonus question, but just so you know, this is just to get you guys really thinking about these problems. Okay. Any questions about this problem in particular? Yes.
Somehow when I was calculating the current for the branch that had R6 and R7, I got a different current. I got 4.165.
4.165.
Yeah, I'm not quite sure why I got that. I know I'm broken the calculation.
Okay.
I'm not quite sure. I mean, it was within like 7% by the end of it. But
Right. So you ended up with the 476 going through this branch.
yeah, I'm not quite sure like what my mistake was.
My guess is you probably grouped it together, either doing the 2.0 or the 1.5. My guess is probably the one used the 1.5 instead of the total 3.5 for that branch. That is my guess.
Okay, that makes sense.
Just because that's where it would put those values close to where we were looking. So we got to remember, you have to use the entire branch resistance when you're using current divider, not just the first resistor in that branch. Which, like I said, I think that's what that numbers wise sounds like what it would be. Okay. The next one we're going to talk about is using our potentiometer to make a parallel circuit. That style is one I like to do. Those ones I like to do for fun, just because you can start getting some really complicated circuits to try and figure out what is my total resistance, what's in series, what's in parallel, how can I solve for this guy. Those are ones I would used to do just for fun because I was trying to practice, different combinations of series and parallel and all this stuff. So our circuit that we have is this. We have R1. We have our potentiometer here. And then we have two resistors in parallel to our potentiometer. R1 is 2.2 kiloohms. We have 47 volts. R2 is at 10K. R3 is 1.2 kiloohms. R4 is 3.9 kiloohms. And we want, so we'll label these guys, A, B, and C. RAB is at 25%. What I want to know, what is the R total? What's the voltage drop across R1? The voltage drop across RAB? The current through R3? And the power of R4. Huh? Why? Just because my color choice? Satan. The wrong emphasis on the wrong syllable.
So all the answers are relative to the potentiometer being at 25%.
Correct. With AB being at 25%, more specifically.
And it gets worse from here?
Not necessarily worse. More fun.
For you.
Well, in general. So give everybody a chance to start working through this. Huh? Oh, you're good. You're good. Hmm? Yes, current of R3.